happy to have Vijay Balasubramanian from Pennsylvania. And I'm sorry about my mistake in the time zone understanding, but I'd like to thank Vijay for kindly connecting 2 hours before the suggestion. Thank you very much. So please start your talk. His talk, the title of his talk is, if it's as scheduled.
It's the quantum complexity of time evolution. I can't remember exactly what it may have been a slightly different title.
Thank you with chaotic Hamiltonians. Okay, so please start.
Okay, great. So thanks very much for the invitation to speak at this conference. I think I might have spoken at one of the much earlier versions of this conference, possibly in Seoul itself. That was a really, really wonderful visit. I wish I was there again. But anyway, here we go. So today I'll talk about the quantum complexity of time evolution. And this is work done with my collaborators, Matt DeCross and Arjun Kar, who are graduate students with me. What's that? Sorry, I'm hearing someone else's voice. Was there a question?
Okay. So please turn off all mic now, the audience.
Okay. Right, fair enough. So, so this is work done with Matt DeCross and Arjun Kar, who are graduate students with me, and with Onkar Parikar, who is was a postdoc with me and is now currently a postdoc at Stanford. Okay, very good. So, so what's this talk about? So as all of us know, in many branches of physics, we talk about complex systems as a thing, and complex systems are clearly things that have many internal components, many body interactions of different kinds, multi-party correlations, and emergent behaviors that we're interested in. And typically when people talk about complex systems, they talk about stuff like problems in biophysics, like the dynamics in cells and strongly interacting materials. But of course, in our fields, we're interested in things like black hole microstates, which are in some way clearly very complex systems, and things like ADS-CFT and emergent space-time. So in particular, as I think everybody in this audience knows, there is a particular conjecture that maximally chaotic systems have complexity growing linearly in time, and that this complexity may be realized in the ADS-CFT correspondence either in terms of the volumes or the actions or something associated with the bulk space-time. So trying to understand this kind of thing in detail, there are many challenges to that, but one of the basic challenges is the question of how complexity is defined as a thing in quantum field theory, and questions like, can complexity be used, for example, as an order parameter to separate integrable and chaotic theories? So we'd love to know some technical definition, some concrete definition of what we want complexity to mean, and thereby to try to think about how to evaluate these sort of various conjectures about the nature of complexity in things like chaotic systems. So we can take a cue from ideas in computer science and information theory, where the notion of complexity is essentially defined in terms of the size of an object or of a computation that needs to be done. So for example, Kolmogorov defined the complexity of an object, like a number, like pi, as the length of the shortest program that's required to produce it. So for example, from this point of view, a random sequence is very complicated, but pi is pretty simple because there's an algorithm that makes it. Similarly, there's the notion of stochastic complexity in coding theory, where the complexity of a message is the size of the smallest code to give a compressed description of that message. So again, it's the size of the thing describing the message. So in computer science, we talk about the complexity of classes of problems. So a class of problems is you have an input and you have to compute an answer for that input. And the complexity of the problem class has to do with the size of the smallest program that calculates the answer. So in the language of circuit complexity, which we've been using a lot lately in physics, if you have a bunch of input bits, a bunch of qubits, if it's quantum bits, then you imagine a bunch of gates, and the gates sort of cascade up, and then you can say that the complexity of the problem class is some function f of n, where fn is the number of input bits, and it's measured by the size of the circuit, maybe the number of gates or the depth of the circuit or something like that, that's used to compute the answer. Now, by the way, feel free to ask me questions at any time during the talk. And I know the talk is half an hour, and then there's a discussion session. I think, if I understood correctly, that's 20 minutes or 30 minutes afterwards. So we can use some of that discussion session during the talk if you want. Okay, so this is the notion of circuit complexity. So for us, what we're interested in the context of physics is the complexity of quantum mechanics considered as a computation. Is there some way for me to move this little frame here? Maybe there is. Okay. So we'd like to think about quantum mechanics, quantum mechanical time evolution as a computation, and think about the complexity of the process in the same senses as in computer science. So, okay, how does this work? I imagine some initial state consisting of some qubits, zeros and ones if you like, or up and down spins. And then there's a time evolution. The time evolution operator is U. It carries out a computation. And at the end of the computation, you have a new state psi of t. So we'd like to know, is this a complicated time evolution or is it a simple time evolution? So how would I think about this? So intuitively, suppose you had a time evolution that took a sort of wave function, let's say, that was had a bump like this and turned it into something like this one over here with these few bumps like that. Then we might be tempted to say that this is a simple time evolution because it leads to kind of small local changes in the wave function. By the way, are you able to see my cursor? Because I'm pointing to things and I want to make sure.
Yeah, we can see it, yes.
Great, excellent. Okay, good. Now, but what would be a complicated time evolution? Well, suppose I started out with some nice simple wave function like this, and that after a while, time evolution took it to some very complicated bumpy thing with lots of non-local entanglement. Then we might say that this seems complex because there are large local and global changes and substantial non-local correlation and entanglement. So that seems like some kind of complex state. Okay, so given that intuition, how could we construct a measure of the complexity of systems like this and relate it to other properties of interest in physical systems? Now, I'd like to distinguish two possible notions. One is the notion of complexity of states. That is to say, someone has made, let's say, this state on the left with a couple of bumps, and someone has made this state on the right, which is very complicated with non-local entanglement. And we could say which one is more complicated. So that's fine. You could do that. But in some ways, the more interesting thing is to ask, what does physical time evolution do? Where it's sort of more interesting to consider states that are naturally produced by time evolution because, well, that's what physics is about. It's about time evolving of states. So we'd like to understand. So perhaps a better notion that we might care about is we could consider the time evolution operator, namely e to the minus iht, and ask how complex the evolution generated by this operator is. So in effect, we want to ask, what is the complexity of the operator, time evolution operator, e to the minus iht? So that's the question we're going to go after because it tells you something about the computation that's being performed. This computer, if you like, e to the minus iht, takes in an arbitrary input state, produces an output state, and we want to know if it does that in a complicated way. Okay, so how do you do that? So we can take a cue for thinking about this. Some work.
Okay. May I have one question about this? Yeah. Yes. So this intuitive understanding of how the state evolves in time. Yeah. I think one issue is how you consider the unit of complexity. So, for example, if this state is very long, then the complexity may be long. However, this time evolution complexity would be not relevant about the size, maybe.
It's possible. So there could be different notions of complexity that are relevant in different ways. I'm trying to make an argument for this particular notion of the computational complexity of time evolution. As I said earlier, you could, of course, if you take a state made of many qubits, there's some scaling with the number of qubits in the state. That's a system size scaling. Yes. It could also be, right? And but you could ask, given a system size n, you could imagine different time evolution operators that have a different amount of complexity relative to each other, right? So
whether we normalize it by n or not is actually up to us. What kind of?
It could be up to us, right? It could be up to us. Maybe we want to do that. Maybe we don't want to do that. So I think to some degree, it's not completely obvious that the different notions of that there is a single notion of what we want to mean by complexity. Different notions could be useful for different purposes. Personally, I think it's still early days. So perhaps the kind of definition we're trying to come up with makes sense. Perhaps it doesn't make sense. In the end, the value of the definition is in its uses, So just to expand on that, if you take a course in analysis, at some point in the second week or something, they tell you the notion of a compact set, right? Every cover has a finite subcover. And if you're like me, I looked at that and I was thinking, what the heck? Why would anybody care about this crazy idea? Well, you care about the crazy idea because if a set is compact, it contains its limits and all good things in calculus follow. Right? So the value of a definition is in the theorems you can prove with it. So it could be that, right, one notion of complexity is useful for proving this, and one notion of complexity is useful for proving that. And it's up to us yet to understand if there's a relationship to volume or to action ADS-CFT, which notion of complexity. Anyway, I'm going to try to define something that we can say something about, and try to make some progress. That's all. Okay. So keep trying to shrink this. Okay, great. There we go. Let's take this down here. So, okay, so how would you go about defining complexity of time evolution? So here I'm going to imagine that I have a Hilbert space, and the Hilbert space has n/2 qubits. That's because later on I'm going to talk about the SYK model. So I have, it's a product of, complex planes. And so then the unitary time evolution basically is some SU2 to the n/2, the action of an SU2 to the n/2 on this Hilbert space. It's a unitary transformation of the space where I've dropped the overall phase. So the difficulty with thinking, and then time evolution is like a trajectory on the space. So U of t is some operator, is some object in SU2 to the n/2, and you have a trajectory that is the time evolution. Now, the difficulty with thinking about this trajectory is as follows. If you were talking about SU2 is simply S3, that's simple, it's a sphere. But in general, SUN is some complicated fiber bundle. And so because of this, it's difficult to think about what these trajectories are and how they work and so on. In any case, suppose you wanted to know how complicated is the trajectory U of t, you might imagine that taking a Q from the computer scientist, you should just basically ask, how many separate operations do you need to get from the identity to U of t? So you might ask, if there's many infinitesimal steps, somehow it's more complicated because you need many steps to get through this curve. So in some sense, it's like the length of the curve. So this is an idea that has been described before in computer science in quantum computation by Nielsen and others, with the idea that if you have U of t describing a trajectory like this, and let's say U of t has brought you to this point here, that the complexity of this operator should be understood as the length of the shortest path in the unitary group that will lead you from the origin to this point. So the shortest path measures the least number of operations you need to perform to get to this operator from the identity. In some sense, that ought to be the complexity of this operator U. So that's the idea, right? So this is the kind of notion that Nielsen tried to use. And in particular, Nielsen argued that if you pick the correct metric or some class of metrics on the unitary group, that this notion of geodesic length on the unitary group space is equivalent, is polynomially equivalent to quantum circuit complexity, right? So he was actually interested in the discrete complexity associated with the circuit complexity and felt and showed that this was polynomially equivalent. But in physics, we're in continuous time, not in discrete time. So in some ways, it actually seems like the geodesic length on the SUN manifold seems like the right notion of complexity in the first place. So the key question is, which metric should you compute the geodesic length in? So let's think about that as follows. So infinitesimally, if you have an infinitesimal motion here, the infinitesimal motion is described by some operator, VI, TI, where TI are the generators of SUN. And I might divide the generators of the group, the unitary transformations, into simple operators and complex operators. So a simple operator, we could take, for example, to be a k-local operator, namely one acting on, say, less than or equal to k elements. Now, if the system has, a spatial organization, you might further require that these generators should act locally, physically. But here I'm imagining some qubit system, so I'm going to define simple as acting on less than k elements. And complex is not k-local, so it acts on many elements at the same time. So there's a very practical sense in which even if you were building a quantum computer, this is a useful notion of complexity. So for example, suppose you have a gigantic, if you look at many of these quantum computation setups, it's like a gigantic room with, cryogenic things everywhere and, little ion traps and laser cooled things everywhere. So in such a system, suppose you want to manipulate the system. Well, if you need to manipulate many bits, many qubits at the same time, it's harder. And if you have to manipulate fewer qubits at the same time, it's just easier to make the device. So there's some very practical sense in which defining simple in terms of k-local or not k-local makes some sense. Anyway, following Nielsen, we are instructed that the useful metric to consider is we want the metric to be small, or order 1 in the k-local directions, and large in the other directions, of order e to the s, where s is the log of the dimension of the Hilbert space. And if you pick a metric of that character, then the geodesic length in the unitary group will be polynomially equivalent to quantum circuit complexity, which is to say up to some polynomial, it will be the same thing as the circuit complexity to compute the, in this case, the time evolution. Okay, so this is supposed to trying to capture the idea that an operation is complex if you have the correlated action on many elements, and it's simple if you do not need correlated action on many elements. Given that setup, that we're going to think about complexity as the length of the shortest path or geodesic on the unitary group in some metric which punishes that says that k-local directions have an order 1 metric and non-k-local directions have a big metric. Given that definition, basically what we will show is that there is always a linear geodesic, by which I mean the following. If the Hamiltonian is built out of simple generators in this way, it's J alpha, T alpha, sum on alpha, then there is a geodesic on the unitary group, which will get you from the identity to the time evolution operator with a length or complexity, if you will, which is the time times the square root of the sum of these coefficients. So that's a statement that there exists such a geodesic with linear growth of the complexity in time. There's a second statement that you can show, that this linear growth in complexity persists for a time exponential in the entropy, in the log of the dimension of the Hilbert space, up to certain global obstructions, if a particular condition is satisfied. We're going to call this condition the eigenstate complexity hypothesis. And so the way we should, there's a complicated expression, so let me break it out for you. So M and N here are energy eigenstates of the system, and alpha, T alpha, are the k-local generators, and T alpha dot here are the hard generators, the hard directions where you have to manipulate many bits at the same time. So we can show that up to certain global obstructions, the linear growth in the complexity of time evolution persists for a time that's exponential in the entropy, provided this quantity RMN is of order e to the minus 2 times the entropy times some polynomial in the entropy times some numbers of order 1. So what is RMN? Look, the numerator involves the matrix elements of T alpha of the simple generators taken between different eigenstates, right? So M and N is between eigenstate M and eigenstate N. So you take this thing and you square it and sum over all the simple generators, and then it's normalized by sum over all the generators, both simple and hard. So we can show, and so that we can show that this is true. Okay, and we can also further show that this condition, the ECH condition, is satisfied by the SYK model for large N. I will not have time to discuss that today. So what does this mean? So here's this condition again. So it means several things. So suppose you satisfy this ECH condition, then up to certain global obstructions that we will talk about later, the linear growth of complexity persists for an exponential time, as you'd expect for black holes and for chaotic theories. That leads us to suspect, of course, that this condition is satisfied for chaotic theories, but may not be satisfied in general for integrable theories. So what does it mean intuitively to have this condition? So if you look at it, the numerator here says, if the numerator here is large, it says that a local operation can move you between energy eigenstates, right? So what the fact that this quantity is small says that local operations cannot move you between energy eigenstates. So that's the sort of physical content of the system, of this criterion. So if you satisfy this criterion, again, the local operations don't move you between energy eigenstates, you can guarantee linear growth of the complexity for a long time as expected in holography. So that's the result, and I wanted to present the result first because it's a short talk, and actually, nominally, I'm out of time. So I want to find out how many minutes I have left, and in that time, I will tell you a compressed version of how to arrive at these results. So one of the organizers should tell me, given the late start, how many minutes do I have now?
Because of my mistake, talk started, I think, 10 to 15 minutes later than the scheduled time. So you have still 10 to 15 minutes.
I'm going to interpret 10 to 15 minutes as 15 minutes.
Yeah.
And I'm going to use the 15 minutes. Okay, great.
Before that, let me ask a question here. So in a concrete example of SYK, for example, what's the difference between your simple generator and hard generator?
How many fermions you act on at the same time?
Oh, I see. So since I have a concrete Hamiltonian, so say SYK4, then we have interaction term that is 4 fermion, right?
Yeah, so that's a simple operator because it does 4 fermions, let's say.
Oh, I see.
Let's agree that that's simple for now. But if you wanted to consider a term that acted on 8 fermions because there are n fermions in the system, then that would be, let's say, a complex operation.
Oh, so in the case of SYK4, everything is in easy generators?
Well, it depends.
In the Hamiltonian.
In the Hamiltonian. Well, you don't have to say that the Hamiltonian is easy, but we're going to say that the Hamiltonian is easy. That it defines what locality means.
So I'm particularly interested in how to evaluate this matrix RM.
I am going to show you.
For the case of SYK. Yeah. So,
yes. So we did that explicitly. So I won't describe the SYK model in, well, you can look in the paper for the explicit calculations with SYK, but I hope I will give you much more detail in a minute or two on how to actually evaluate the quantity. Because the nice thing about this quantity is you can calculate it. In some cases, you can calculate it by hand and explicitly. In other cases, you can definitely calculate it numerically, and you're just limited by how many dollars somebody gives you to spend on your university's cluster. Okay. So it's a practical criterion, which is very helpful, as opposed to a spiritual criterion which you can't evaluate. Okay. All right, great, wonderful. So again, let me try to close this and move this out. Okay, so in the 15 minutes that I have, I'm going to try to give you a flavor of how you actually arrive at these results and how you do computations of these things. So our goal at the technical level, what do we need to do? We need to evaluate geodesics of SU2 to the n over 2, right? So for SYK, so we'll do SYK as the kind of example. So SYK here with n Majoranas has a Hamiltonian that looks like this. So you have psi I through psi IQ and I1 through IQ. These are the coefficients of these terms. You have n fermions, and you've got various kinds of terms built out of the n fermions. And Q defines how local these terms are, how many fermions are involved in these terms. And we draw in the traditional SYK model, you draw these coefficients J randomly from a Gaussian with some variance, and the variance is to scale with that. Fine. So the unitary group is here, SU2 to the n over 2, dropping the overall phase. So we need to discuss motions on the group. We need a basis of generators. So one basis of generators we all are aware of are the gamma matrices. And so we take the gamma matrices 0 to n minus 1. They satisfy this algebra. Gamma A, gamma B is 2A delta AB. And if you, in your head, how are these gamma matrices represented in the SYK model? Well, you can take the gamma matrix gamma A to be like psi A, and then the algebra of the fermions effectively realizes this algebra of the unitary group. Now we're going to use a slightly different basis that's actually more convenient for our calculations. So the basis we're going to use is we're going to take products of these gamma matrices, so products of the fermions in some ordered way. And I'm going to give these products a name. Ta1 through Am will be Ti, where I is a sort of composite index A1 through Am. And you can similarly show with a little work that this Ti forms a convenient basis actually for SU for the unitary group. So the next thing we need to work out geodesics on the group is we need a metric on it. So this is so let me tell you how we do that. So how would we construct a metric? Well, with these generators, the commutators realize the algebra Tij is equal to the structure constants times TL. And so, the conventional traditional metric that's usually useful is the Cartan killing form, where you take some quadratic sum built out of the structure constants, and that's Kij, the Cartan killing form, which is acts like a nice metric on the unitary group. We, however, are going to sort of follow the idea coming out of the computer science literature that you need to have a metric that, you know, is large in the hard directions because it's hard to go in that direction, and is small in the easy directions because that's easy. Okay, good. So we're going to modify this metric, the Cartan killing form, by multiplying it by Ci plus Cj over 2, where Ci is chosen to be 1 for k local direction. So the example, for example, we were discussing earlier, maybe k is 4. So if you have, so for things that are products of less than 4 fermions, this would be 1. And it's 1 plus mu, where mu is exponential in the entropy for all of the other I. So we're going to take it like that. Okay. So now I've described the metric here at the identity. So this is at the tangent to the identity. So really, if you have at some other, if you're elsewhere in the group and you have tangents x and y at that point in the group, really to describe the metric, well, the way I'm going to do it is I'm going to take these tangents x and y, I'm going to pull them back to the identity, and then having pulled them back, then you compute this metric there, and that's our definition of what the metric is going to be. So this is going to be a metric that, you know, in the hard directions, if it's more than k local operation, you'll get a big number in that direction, and for a k local or less direction, you'll get a, you know, something that's order 1 in the metric. Okay, so the geodesic equation on SU2, and you can now just do, you know, just go and write down the geodesic equation. So you do that, and this was done before. There's a thing called the Euler-Arnold equation, which is the geodesic equation on a group using the Levi-Civita torsionless connection, and it looks like this. So here, Vi, Vj, Vl are tangents to the path, and you solve this differential equation. This is just the standard differential geodesic equation written out in some convenient way. G is the metric we spoke about before, and you're supposed to solve this, and the path-ordered exponential will solve this equation. Okay, and hard to compute, but there's a procedure here. So we need to solve this equation with the boundary condition that u of 0 is the identity, and that u of 1 is the time evolution operator e to the minus aht. That's our goal. And the complexity gets defined as follows. So, you know, given between these 2 points at u of 0 and u of 1, there may be many geodesics, and we're supposed to compute the length of those geodesics and then minimize over them. And that's supposed to be the target, the complexity of the target operator. So that's our definition for what we're going to do. As what we can see, you know, it's all completely practical and, you know, just defined. Okay. Let me just give a very simple example. We're not going to work through this example in detail because there isn't time, but I'll just to give you a flavor. If this was SU2, so SYK with 2 fermions, well, T1 would be gamma 1, T2 would be gamma 2, and T3, the third direction, would be I gamma 1, gamma 2, and you could decide to call that a hard direction if you liked. Then the Cartan killing form is diagonal, it's delta ij, and this metric that we defined is diagonal, except you know, the hard direction has a 1 plus mu in it. All right, so that's what you'd write down. Then what are you supposed to do? You're supposed to say, well, any given operator lies along the, you know, the tangent directions in the group. You could the geodesic equation that we discussed earlier, that we described, where was it? Over here, simplifies, and it becomes 3 equations like this. They're easy to solve. You can work out their complexity. You can do all of this completely by hand and calculate everything in detail. So it's interesting. It's not really the problem we want to talk about because this is not a chaotic system, etc. So I'm not going to discuss the results about that in detail. We developed those more in the paper just as a worked example, and in a very practical way, you can calculate all of these and find, you know, various kinds of interesting effects like plateaus in the complexity if you average over things and, you know, things like that. But I'm not going to talk about that right now because of the constraint of time. So instead, what am I'm going backward, I think, through the talk, so I had better go forward. So great. So instead, I want to get to, in practical terms, how we arrive at the result that we did. So if we work out for general n, it's of course more complicated than SU2. So if you take the basis of generators as a product of gamma matrices as before, there's a certain amount of fuss and mess about, you know, figuring out the correct sort of representation of it, figuring out the correct, the simple way of manipulating the equations. And I've done that all on this page, just to show you that this is all just a step-by-step calculation, but we don't need the details of the calculation. So I'm going to tell you the result of calculating the geodesics on this space. So one solution to the geodesic equation, as described a moment ago, is the following. So imagine that the Hamiltonian is an easy operator. Then it turns out that one solution to finding a geodesic between the identity and the time evolution operator is basically to sort of flow straight in the easy directions along that way. Okay, so there is such a linear solution always. So specifically, if H, the Hamiltonian, was K local, so it's J alpha, T alpha, something alpha, then the target you're trying to get to is e to the I, V alpha, T alpha, S, where S is the parameter along the geodesic, and you want to get V alpha as J alpha T, because you've evolved for a time T. You can show that there is a geodesic in which you just shoot along the Hamiltonian and it'll get you to the correct point. Not surprisingly, because we agreed that the Hamiltonian was a simple direction in the tangent space of the unitary group. So if this is the shortest geodesic, you would come to the conclusion that the complexity will grow linearly in time. You can just plug this in, it's easy. So really, the question we need to answer, and that's what the holographic expectation for chaotic systems is supposed to say. So the question we have to answer is, under what circumstances does this linear geodesic with this linearly growing complexity remain the shortest geodesic? What obstructions are there to that? And you could basically imagine two. One kind of obstruction you could imagine is a global obstruction where there's a geodesic loop of some kind. So basically, you're going this way from there to from the identity to the time evolution operator, but somehow there's another path that goes like this in some other way along the group. Remember, the group is compact, so there could be another path somewhere. That global problem is very hard to address, and we will not address it here. But there's actually another practical obstacle that can appear and does appear, especially in integrable systems, right? And the other practical obstacle is something called a conjugate point. A conjugate point is like this. So you have the original straight trajectory from the identity to e to the minus IHT. It's possible that you could sort of bend the trajectory a little bit, and there may be another geodesic that sort of starts here and then winds up intersecting the original trajectory here. And then you can deform this kink to get a shorter path at second order in the perturbation. So this is something called a conjugate point. And so what we're going to do is to set up a condition to ask that these conjugate points should be avoided. Okay. So how do you find conjugate points? Well, fine. It's just the same geodesic equation again, except what we need to do is the unperturbed. So we start out with the geodesic, which is this linear trajectory along the Hamiltonian. And the idea is, you're supposed to perturb the geodesic a little bit and then see where it winds up. So you take the perturbation of aiming the geodesic initially a little bit away. So that's this delta V of S. And then you need to integrate forward along that slightly perturbed trajectory to see where it goes. So that first order perturbation of the Euler-Arnold equation, of the geodesic equation, also has a name. It's called the Jacobi equation. And again, there's some complicated series of equations involving commutators, and in this case, the Hamiltonian and so on. We don't actually need the details of that. Again, I'm going to try to tell you the answers just because this is a short talk, as opposed to working through how the calculation goes. So believe me that there's a first order perturbation of the geodesic equation. And if you solve it, this is what you get. This is a complicated slide. So I'm going to try to sort of walk you through the relevant piece of this complicated slide. So remember, we want to start here at identity, and we're hoping that there is, or we want to check if there is a conjugate point. So namely a trajectory that goes in some other direction and then winds up intersecting the original trajectory. So what this would mean is that you wind up, well, normally if I perturb the direction a little bit and then evolve this for a certain amount of time, then what would happen, or over a certain distance, then you'd wind up perturbing the final operator that you get to. So I'm going to multiply both sides by U inverse, and we would get a conjugate point if U inverse delta U is equal to 0. That is because you wound up at the same point, so this perturbation here at the end of the time is 0. So the way we're going to think about this is as follows. We're going to think about a super operator that takes operator perturbations here, like delta V is an operator perturbation, and maps it to the final perturbation at the end of the trajectory. So it's going to map operators to operators. So there's a super operator that maps operators to operators. So it turns out that with a certain amount of pain and suffering, you can actually work out an explicit expression for this in perturbation theory along the original linear geodesic. And that's this complicated expression here. Don't worry, we're going to simplify that in a moment. But there is a complicated expression that's completely explicit. Okay, there are two ways to simplify this expression. The first way, which gives us intuition, I should say. So if I think about the super operator mapping an initial perturbation to the final perturbation, then what we're looking for is delta V's that are zero modes of the super operator. So basically, if I have an eigenstate of this y mu, the super operator, that has an eigenvalue 0, that tells me that after the time has elapsed, I wind up again at the same point. So we're looking for 0 modes of the super operator. Okay, so we're going to look at that in 2 cases. The first case is where all directions are easy. So that's the case where the metric on the space of the unitary group is just the Cartan killing form. So it turns out in that case, the super operator is extremely simple. It's just the time evolution, if you like, of by conjugation of the original perturbation. So you can do some work and you discover that the eigenvectors of the super operator are then the projection operators of the theory, namely operators mn, where m and n are energy eigenstates. And then you can further work out that the eigenvalue associated to any one of these projection operators, so to any one of these eigenstates of this super operator, has the following form, where you have e to the I delta mnt minus 1 divided by I delta mnt, where delta mn is the gap between the 2 states that are there in the projection operator. So if you want to get the first time, so when is phi mn, this eigenvalue, equal to 0? Well, it's equal to 0 when t, the time t, let's call that tmn here, is 2 pi over delta mn. That's what's being said here, right? Fine. So the smallest time you can get is when the gap in the denominator is as big as possible. So you take the maximum energy within this finite space of states and the minimum energy, so that's the biggest gap. So it's 2 pi over the biggest gap, and that tells you when the first conjugate point will happen. So you see, for SYK theories, this gap between the highest and the lowest state is of order n. So what this is telling you is if all directions in the SYK are considered easy and are not hard to go into, then the first conjugate point happens very quickly at a time that's decreasing in n. Now, the second thing we should consider, that can really care about, is a situation where the k local directions are easy and everything else is hard. In this case, to simplify this, the expression for the super operator, we do the following thing. Suppose you assume that this ECH, eigenstate complexity hypothesis criterion, is true. This is the criterion that's stated at the beginning, where you have various kinds of overlaps of energy eigenstates sandwiched with, the simple operators, and that this thing should be exponentially small. So if you take this as condition as given, it follows that the super operator, again, after some work, you can show has eigenstates, which are, again, the projection operators mn. M and n are energy eigenstates. And the eigenvalues take the form given in this expression. So I'm going to copy that expression over here. This is the form of those expressions. And so you want these things to be 0 to get a 0 mode. And what do you get? You want this exponent here to be 2 pi. So you want the time here in this exponent to be 2 pi times 1 plus mu. That's the thing in the denominator, divided by delta mn. So now mu is the e to the s, is the thing that punishes the hard directions in the metric. So now if you put this in, you'll get that the conjugate point, the first conjugate point occurs at a time 2 pi over the maximum gap in the system times something that's exponential in the entropy of the system. So what you find is that it's exponential in S. So as long as the gap does not scale exponentially in the number of things, of objects in the system, like the number of fermions, you have that the linear geodesic that led to linear increase in complexity, that geodesic is minimizing for an exponentially long time. So that's what we wanted to show, and that's what we've just done. Let me conclude. So I discussed 3 things. So one is there is always a linear geodesic. That's this thing where if the Hamiltonian is easy, then there is a geodesic from the identity to the time evolution operator with the complexity growing linearly in time. This linear growth in complexity persists for a time that's exponential in the entropy up to global obstructions. If this ECH criterion is satisfied, this ECH criterion says that it is very hard, exponentially hard, to produce transitions between any 2 energy eigenstates using just simple operators. That's what this criterion says. For a third thing, which I did not show because there was no time, is SYK for large n satisfies this condition so that holographic expectations for complexity growth are matched. That's a numerical analysis. And if you're interested, you can look at our paper. So these results actually have implications for quantum complexity class separations. So for anybody who's interested, for example, there's a famous question about whether or not the complexity class P space is or isn't a part of BQP/poly. So P space is the set of problems that can be solved in the classical computer with space polynomial in the problem size and as much time as you need. So this is a vast class of problems. So BQP/poly is the so-called bounded error polynomial quantum problem class with polynomial size hints. What that means is that you do a quantum mechanical calculation. The error is bounded, so you promise that the calculation is designed so you don't make mistakes because of quantum randomness beyond a certain fraction of time. The size of the circuit is polynomial, and polynomial size hints means you're allowed an auxiliary hint system that gives you hints that are polynomial in the size of the problem. Fine. So the question is, is this inclusion true or not true? Okay. So Scott Aronson and Lenny Susskind have a statement, have a proof that P space is not contained in BQP/poly if and only if the complexity of the time evolution operator after an exponential time is larger than any polynomial n. So what we are showing is that up to global obstructions, if a theory satisfies the eigenstate complexity hypothesis, then the complexity does become exponentially large after an exponential time. So this is consistent with the conjectured non-inclusion of P space in BQP/poly. So this is just to illustrate that we're physicists and we're really interested in the consequences of these kinds of things in physics, but actually these kinds of results actually have some kind of bearing on classic questions in computer science. Okay, I will stop there because I think I am out of time.
Thank you very much, Vijay. Okay, so shall we have a discussion, a question session? So if you have any question to Vijay, please.
Oh, hi, I have a question.
Yeah, please.
Yeah, so how do you expect the eigenstate complexity hypothesis to be violated in integrable systems? I understand it's supposed to be satisfied by chaotic systems.
Yeah.
I just don't see what should be different in integrable systems. It's not small.
So it's not. So first of all, I should say that the way we made this criterion is if this is true, then something is true. It's not the converse. As in, if this is true, then you have this exponential complexity growth. So a way in which this can be violated in integrable systems is it does not have to follow that this is exponentially small with an exponent of e to the minus 2 times the entropy. Right? This is a very, very heavy suppression, right? And it doesn't have to be like that. The difficulty, so we've actually tried checking this. So a very nice thing to do would be to take an like a spin system, which has both some free spin system that has both integrable and chaotic deformations, and then ask how this thing works. So actually, there's a student, Kathy Liu, in my group who has been thinking about that. And at least in our hands, we're not numerical calculation experts. One of the challenges with doing that is if you have a finite system, how do you know what's exponentially small, given that there are order 1 fluctuations? So there's some. So overall, things are kind of in the right ballpark for us, but we're not entirely sure how to check that. So what you'd rather do is to be able to prove things more explicitly. Okay. Another subtlety is that actually many integrable systems can act remarkably close to chaotic systems, at least in some of their coarse behavior. So even if you go look at the papers of Rigol on the eigenstate thermalization hypothesis, which is supposed to be a criterion that looks different in some kind of integrable or chaotic and other kinds of theories, it can be very subtle to determine that it's showing the the ETH is really being satisfied and not satisfied, and is it not for the integrable system versus the chaotic system? Part of that is involving the thermodynamic limit. It's really, these statements are ultimately kind of large n type statements, and it's very hard to check that. But there's a subtlety, because if you have an interacting integrable system, you can have a very, very complicated spectrum. It may not satisfy the same kind of level repulsion that you tend to see in chaotic systems, but it can be very complicated, right? And very dense. Yeah. And so that can produce the difficulty. So I think I'm trying to say that it's not necessarily, okay, so we'd like to conjecture that this sort of criterion would separate integrable from chaotic theories, but checking that is going to be complicated if you're going to use, it's definitely true for free theories, right? As opposed to the chaotic ones. But really the interesting ones are the strongly interacting integrable theories. And we're still looking for a way of checking the criterion there. And if anybody has any ideas, I'd be very glad to talk.
Yeah, so I was maybe massive deformation of SYK would be a way to check it. I don't know, because if this massive deformation is very large, maybe the system becomes less chaotic. So maybe that,
yeah,
I don't know if that's.
Perhaps, again, that would involve some kind of numerical calculations, but perhaps that is one way of proceeding. What you're pointing to is you use the term less chaotic rather than integrable.
Yeah.
Indeed, I think that's an interesting point, that because, we often talk about chaos versus integrability, but actually, if you look at many systems, like for example, even the kicked rotor, classical systems, which are chaotic, so you start off in one limit of the coupling, and the thing is not chaotic, right? Then as you increase the coupling, you'll find these islands in its phase space of chaos. So most of the configuration space is not chaotic, but there'll be these little islands that are chaotic. And then when people usually say that, oh, beyond this parameter, the thing is chaotic, what they mean is it's chaotic everywhere, or nearly everywhere, right? No matter where you start the system, it will behave in a chaotic manner. But what that points to, I think, is that there is such a thing as a degree of chaos, right?
Yeah.
Somehow, you can have maximal chaos. You can have chaos everywhere in the phase space. You can have chaos someplace in the phase space. So I think we need more refined criteria than we've been using to classify the degree of chaos. So another idea that has been sort of floating around the back of our head is that perhaps criteria of the kind that are being described here, like these kinds of conditions, right? Conditions on how easy it is to go from eigenstate to eigenstate, stuff like that, with different things on the right-hand side, rather than this e to the minus 2s, could be kind of, order parameters for different degrees of chaos. So that's all things that we haven't elucidated yet, because we are in fact trying to work out some examples using spin change, things like this. But I think really what we need is a body of examples where we evaluate these things at different, in systems with different, amounts of chaos according to some criteria, and try to see how this separates it.
Okay, so thank you very much for explanation.
Thank you. So is there other question? Okay, I have more questions, but before that, I think it's better to close this session formally. And then after that, if Vijay is still here, we can ask questions. Okay. So let's thank Vijay again. Thank you very much.
Well,